Last year, during my trip to Silicon Valley, I was invited to visit a company called Squantum. When you think about quantum computing, your mind might conjure up those chandeliers, qubits plunged to super cold temperatures. Squantum is working on something a little different, quantum computing using photons. In this video, a form of quantum compute with intriguing possibilities. Does it quote-unquote work like silicon does today? Is quantum compute really here? I can't really answer those questions in this video, but we can explore the ideas, and the ideas are certainly mind-bending. Quantum computing concepts are pretty intense. There are people who have spent their whole career studying it. I have no intention of covering the whole thing, and I am nowhere near an expert. My goal is to get to where we want to go. Squantum did not sponsor this video, though they did provide me with a reading list so I can try to understand their technology. And of course, I believe that I will make some errors, but that is how the bird flies. I will try to minimize them, maybe with quantum error correction techniques. I want to start with reviewing something we already know well, and then expand on it. Let us look at a regular digital computer. Regular digital computers store information inside a single bit encoded as either 1 or 0. We then manipulate those bits using things called gates. These gates apply logical functions to the bits, creating outputs that we desire. For example, a NOT gate receives a bit and flips it. So a 1 bit goes in and a 0 bit comes out, vice versa. An AND gate takes in 2 input bits, and if the 2 input bits are 1 bits, then it is going to output a 1 bit. If not, then it is going to output a 0 bit. So a 1 bit and a 0 bit gets you a 0 bit. There are a variety of other gates out there, NAND, OR, NOR. Note that a few of these gates are nonlinear, meaning that their output is more complicated than simple addition. This is only possible because the electrons inside the transistors, or devices or whatever, can interact with one another very strongly. If they didn't, then a 1 bit and a 0 bit entering into an AND gate will output a 1 bit. It doesn't, since the 0 bit influences the gate to output a 0 bit. This non-linearity helps give the computer its power. We cannot build the complex logical rules we need for rich calculations without non-linear gates. So, sum it up. We encode data into bits, and then send the bits through combinations of gates and transform them. Such combinations are called circuits. Integrate them all together on a piece of silicon, yada yada yada, and boom, we got an NVIDIA B200, baby. Alright, so now that we have established groundwork in classical computing, we can tenderly step over into quantum computing. Classical computing bits can only flip between 1 and 0, like a light bulb turned off or on, all that jazz. In quantum computing, we store information into physical objects called qubits. These qubits have quantized states that can be the classic binary values, 1 or 0, known as basis states. But famously, qubits can also exist in an arbitrary superposition between 1 and 0 at the same time, like a dim light bulb inside a box that is both some percent on and some percent off. Of course, the quantum part of all this is that if we measure the qubit, then it collapses into one of the 2 basis states. So, it is like as if when we look at the bulb inside the box, then it either brightens to 1 or shuts off to 0. Yes, it sounds weird, but that's quantum for you. Just like in classical computing, we can apply special operations to these qubits. We call these operations quantum gates. Some of these quantum gates are similar to the classical gates we talked about earlier, like the poly-X gate, one of the 3 such poly gates. The poly-X gate acts like the NOT gate in classical computing. It flips a qubit from 1 to 0 and vice versa. But some of these gates do things exclusive to the quantum world. For example, the Hadamard gate maps a qubit into an equal superposition between the 1 and 0 basis states. If we measure the qubit now, it has a 50% chance of being 0 and a 50% chance of being a 1. Another important quantum gate, which we will talk about later, is the controlled NOT gate, or the CNOT. Note that this gate acts on two qubits, a control and target qubit. If the control qubit is in a state called Ket1, then flip the target qubit from 1 to 0 or vice versa. Note that by successfully applying this CNOT gate, we have now linked together two previously independent qubits. This demonstrates another distinctive phenomenon of quantum computing: entanglement. When two quantum systems are entangled, actions or measurements made on one system's state will affect the other. So, after the CNOT is applied and entanglement is achieved, measuring the state of the control qubit instantly tells you the state of the target qubit. This link persists even if the two systems are separated at large distances, making it useful for parallelizing multiple calculations at the same time. In fact, entanglement is necessary to implement economically useful algorithms like the famous Shor factoring algorithm. You know, the one that finds the prime factors of a big number, thusly breaking widely used public key encryption systems like RSA. Now, why would someone want that? So here we have the quantum computing concept in somewhat of a nutshell. We encode data into qubits, apply quantum operations to those qubits, and then measure said qubits at the very end to retrieve the results of our calculations. There we go. So the concepts are out there. Now, how do we turn that into a real computer? Most companies pursuing quantum computing are following what are called matter-based approaches. These use particles with mass, electrons, individual atoms, etc., as their qubits. For example, one such approach is called trapped ion quantum computing. This is where we confine and suspend atoms using electromagnetic forces to produce our qubits. To perform gates, qubits are manipulated with lasers. IBM and Google, on the other hand, rely on qubits made from sets of superconducting circuits called Josephson junctions. Rather than using lasers to manipulate the qubits, we use microwaves. These qubits having matter mean they can interact with one another, so it is also easier to apply quantum gates and entangle them. At the same time, however, these matter-based qubits can also interact with their surrounding environment. This introduces random noise from things like cosmic rays that can alter the qubit's state over time and even potentially decohere them. Decoherence means that the qubit or qubits lose their special quantum behavior and thus their data. This is why these systems need complicated, intense cooling or vacuum systems. It minimizes potentially disruptive thermal and electrical noise. Advances in this area of the industry have made it easier to keep the qubits isolated in the basement on 4chan. The problem is when we need to pull them out and manipulate them to perform quantum gates on them. Actions like entanglement and flippant bits introduce random noise that can cause errors. When such issues happen, we do quantum error correction, techniques that use redundancy to find and correct errors, like how CDs deal with scratches on the disk. While quantum error correction was a significant breakthrough, it ironically enough can add even more errors, so this is not a complete solution. Considering the matter-based qubit's delicacy, the approach that most quantum computing companies are taking has been to start small and grow up. The number of qubits we need to run useful, complex quantum algorithms is more or less 1 million. As I scale up towards that number, new challenges emerge in maintaining control over the qubits and minimizing errors. Google is probably the leader when it comes to this type of approach. In December 2024, they demonstrated a 105-qubit chip called Willow, in which they claim unexpectedly good error correction rates as the qubit number scales. The error correction capabilities seem like a legitimate breakthrough. It certainly did something for the stock, soared 6% the day after the December announcement, and triggered a melt-up in various other quantum computing companies. At the same time, Google's last chip had 72 qubits. Even if the pace quickens, and it will, 1 million qubits seems rather far away. not counting the new challenges that will inevitably arise as we start integrating together so many qubits. Now we can finally start talking photons. Photons have some core characteristics relating to quantum computing. They have no mass, travel at the speed of light, and are relatively easy to detect. Because they have no mass, photon-based qubits have the opposite situation of matter-based qubits. On one hand, it means they do not easily interact with their environment. Quantum information stored in a photon tends to stay there. This lowers the risk of outside noise and decoherence. It implies that a photonic quantum computer can scale to 1,000,000 qubits rather easily. It might even run at room temperature without expensive cooling systems, though there is a caveat that I will need to get to later. On the other hand, though, your greatest strengths are also your greatest weaknesses. Photons are not easily influenced by the outside world. They also do not easily interact with each other, quietly passing like ships in the night. Recall earlier that we talked about the concept of nonlinearity. Without nonlinearity, we cannot build the logical functions that we need to run important calculations. We can produce single photon qubit gates, but if photons do not interact, then we cannot entangle two qubits, and that means we cannot produce nonlinear two-qubit gates like the CNOT. Without that, we cannot achieve the speed-ups we want from quantum computing. For that reason, theorists long believed that a photonic-based quantum computer was impractical. Then in 2001, an interesting paper in Nature by Nil, Laflamme, and Milburn. The paper proposed a setup, the KLM scheme, to do universal and efficient quantum computing using single photons and well-known optical elements like beam splitters and phase shifters. Photons do not naturally interact with one another, but we can make it as if they do. Let me try to break this down. In the KLM scheme, there are qubits represented by a single photon. These are called data qubits, and they are encoded with quantum information using one of two ways. The first is to run them through a polarizing filter. A photon can exist in a superposition of polarization states. When they pass through a polarizing filter, that superposition state collapses to align to a certain direction. So we can say a horizontally polarized photon is coded as 0 and a vertically polarized photon 1. Honestly, this makes more sense when you imagine light as a wave rather than a particle. Luckily, light is both. Another way, and the way more widely used in the industry, is called dual rail encoding. Here, a photon's quantum information is encoded by having it take one of two different optical paths. One path represents a basis state of 0, the other path represents basis state 1. This implies that when the photon is in a superposition state, it is traveling through both paths at the same time. Once we measure the data qubit photon, it collapses per the probabilities of its superposition. So, ta-da, your single photon data qubit. Nothing special about this. We've long known that single photon data qubits are possible. Let's get on to the hard stuff. What about two qubit gates like the CNOT? How do we do that? This is done with a nifty trick. To pull this trick off, we must introduce a set of extra photons called the ancilla photons. These helper photons will play a crucial role in helping us read the whole system. They begin with a known state and follow their own light paths. Using a specially designed optical network made of beam splitters and phase shifters, the paths of the data qubits and ancilla photons are mixed together in a deliberate way to create one very complex superposition between them all. After this, we measure the ancilla photons, not the data qubits, using special single-photon photodetectors set in their paths. This act of measuring the ancilla photons collapses this whole big superposition and gives us information about the remaining data qubits. If the photodetectors observe a specific predetermined outcome in the ancilla photons, then we know that an operation like a quantum gate, like a CNOT, has been successfully applied to the data qubits. We can now use this particular quantum system for later, applying other quantum operations to them. We don't measure the data qubits themselves because we then can't use them for such future operations. If the photodetectors do not detect this outcome, then this particular operation has failed. We discard the whole system and try again. That's the major nature of this process. It is probabilistic. About 25% of C0 gates succeed. For others, it might be even lower. The KLM scheme is rightfully seen as a significant breakthrough in the photonic quantum computing world because it got a nonlinear result from linear optical equipment. But the paper's authors noted at the time of his writing that their setup had no practical applications. And indeed, even after researchers were subsequently able to make gates like a C0 with KLM, using it for circuits and a computer seemed formidably difficult. The problem is that the gates are probabilistic. Creating a quantum circuit out of these gates, like we do with classical circuits, implies chaining together many gates. But you can do the math. If a circuit needs 2 C0 gates and a C0 has, at best, a 25% success rate, then the 2 gates is a 25% of 25% chance. More gates sink the probabilities even further, and those odds are not in your favor. This eventually triggered a philosophical shift away from building big, hairy circuits of increasingly lower success probabilities and instead follow the line of measurement-based computation. Okay, here goes nothing. What follows is an extremely simplified and rough explanation. If you recall, the KLM scheme relies on the act of measurement to perform quantum operations like gates on data qubits. This idea is important. It is almost like as if the measurement act itself is a chisel, chipping pieces off a block of marble to create a sculpture. We can use this to do larger, more sophisticated calculations. We produce a series of small, standardized, entangled bundles of photons called cluster or resource states. These will be primitive building blocks of our calculation. Resource states can take several forms, but the key is that they are standardized, letting us produce them en masse before starting calculations. Squantum wrote about using a resource standard made of 6 photonic qubits entangled together in a ring formation. The 6 photons do not stay together. Rather, individual photons might be routed to entangle with other photons from other resource states. This entanglement is done via the act of measurement. Just like how, with the KLM scheme, the act of measuring the ancilla photons forced the data qubits to entangle and flip. Some of these will fail, and that has been accounted for and dealt with, though you can boost the success rate by adding more ancilla photons. With more measurements, this effectively lets us merge together resource states to create a huge, massive entanglement lattice, a fusion network. And interestingly enough, this does not have to be done at the speed of light. Photons are made, entangled, and measured at our own pace. Anyway, by carefully controlling the sequence of the measurements, you carefully assemble the network, almost like sewing patches together with various interconnections to form a quilt. This final network, or quilt, is the calculation's desired output. We might read all the photons to get a classical type result, or use them for something else we won't talk about in case our brain explodes. Okay, I hope I got that right. If not, well, sorry. I hope I didn't ruin your day. One of the major technical challenges with getting this to work has been producing single photons. Not just any single photons, but identical single photons. We depend on a unique quantum phenomena called the Hong-O-Mandel effect, or Hom effect, which can be observed with an optical thing called a beam splitter. The beam splitter is kind of like a half-silvered mirror. Their job is to split the beam 50-50. Under normal circumstances, half of the photons that hit the splitter reflect back, with the other half going through. Hom effect says that when 2 indistinguishable photons, same in polarization, frequency, etc., hit a 50-50 beam splitter at the exact same time, then they always exit together. There is no splitting, which is what you might expect with classical physics, and this is due to quantum destructive interference. It is through the Hom effect that we achieve this quantum entanglement between photons, and it only works when the photons are indistinguishable from one another. Producing such things is as challenging as it sounds. On the other side, we got to detect these single photons, and the technology for this has been around for a bit longer. The most reliable, apparently, is the superconducting nanowire single photon detector, or SnSPD. SnSPDs are ultra-thin superconducting nanowires with a small supercurrent passing through them. When a single photon of sufficient energy hits the wire at a certain spot, it breaks the Cooper pairs in that area, up to hundreds, causing the superconductivity there to fall apart. So, a little hotspot appears and grows. This hotspot only lasts for a few nanoseconds before it cools down again, but it causes a very small voltage spike that external circuitry can recognize and report as a click. SnSPDs are extremely sensitive, and the industry is rather familiar with them. They're used for LiDAR and satellite applications, for instance. It adds some overhead, I think, but it seems to work fine for Squantum. Squantum was founded in 2015 and has been quietly pursuing the photonic quantum computer for nearly a decade. They recently published a paper in Nature discussing a new manufacturable platform for quantum, Omega. The platform uses commercial silicon photonics processes from global foundries to do all the things we talked about in this video: generate identical single photons, fuse them, move them around, run calculations, and detect them with minimal photon loss. Their office is full of strange glowing systems, pipes, and buzzing equipment. I have absolutely no idea what each thing does, and did not ask about each individual thingy. The startup is developing quantum computing campuses in Illinois and Australia with the goal of providing utility-scale quantum compute to those areas. They're not alone in the photonic quantum space, though I think Squantum is the only one taking this specific implementation. Over in Europe, there's Quandela, and they're trying to build a full-stack photonic quantum computer with the goal of 50 logical qubits by 2028. And the most formidable Chinese effort appears to be the Jiuzhang, built by the University of Science and Technology of China in Hefei. They have built 3 versions of the Jiuzhang photon-based computer from 2020 to 2023. The first version performed a very special task known as Gaussian boson sampling, which is kind of like a quantum benchmarking task, and it did that in 200 seconds. This task would take a classical supercomputer 2.5 billion years to perform. Right now, GBS has little practical application, but it can be useful for determining future quantum-specific tasks. The next 2 Jiuzhang versions have scaled up the GBS paradigm. As I said at the start of this video, I cannot sit here and assure you that the quantum computer is here. There are things we can point to say that it is not. For example, all our encryption appears to remain intact. And Squantum has said that there is more work ahead. They're trying something new, and such path breaking always has issues. There's also the real question of what this compute is good for. Right now, the industry understanding is that quantum computing will not and cannot replace classical computers. They do different things that involve high compute and little memory, since memory right now remains an outstanding question. So LLM AIs like ChatGPT are not in the picture right now. Right now, that universe of tasks is quite small. Cryptography stuff, weather prediction stuff, and drug simulation stuff. So one of the team's longer-term goals is to bring quantum compute capabilities out there in the real world and let developers start to play with it and find out what they can do with it. I look forward to seeing that. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.